Okay, we're going to continue with 1.2, but now we're going to look at this formal definition of limit. And actually, it is best to kind of think of this graphically, and our project is actually going to deal with this, but not quite in this more formal mathematical sense, but in a more applied sense. But we will be doing really what's going on here. And so as we look at this definition of a limit, okay, the pieces are, well, we're going to let f of x, be a function on an open interval. Now, these are some things that you may not think are important, but actually turn out to be important in many definitions and so forth, because if you don't say these things, you can find funny cases that don't work and so forth. So an open interval, right? So an open interval is like, some AB like this. So I'm talking about all numbers in between A and B, but not the endpoints. Okay, so that's an open interval. So it's defined on here everywhere. Okay, let's toss an or defined there. I think they do, certainly. Defined on an open interval AB everywhere, except maybe at C. So they mentioned that C is an element of, so this funny looking E thing, it means it's an element of that open set AB. It's in there somewhere. Now, what the open interval part does then is says that C is not at an endpoint. Okay, so C cannot be equal to A or B because A and B are not in this set. And so if it's an open interval, if it's not A and B, it can't be at the endpoint because there is no endpoint in an open interval, right? I can always get a little closer to B or a little closer to A. And okay, and then we let, L is a real number. That's important, right? So it's not infinity. Infinity is not a real number. So L is a real number. And then we say that this limit as x goes to C of f of x equals L means, okay, and so here we're getting to the real definition part, that for each epsilon, so there's a nice Greek letter greater than 0, there exists delta greater than 0. Okay, so these are two real numbers, and it says for any epsilon greater than 0, there exists delta greater than 0. So this becomes a game. Somebody picks epsilon, and somebody else has to come up with delta. That's sort of the game idea, such that if 0 less than or equal, oops, not less than or equal, less than x minus c in absolute value is less than delta, okay, then the absolute value of f of x minus L is less than epsilon. Holy crap, what did he just write there, right? We just attacked you with math. Now, graphically, though, what this is saying is we come up with an epsilon. Somebody guesses an epsilon. And you look at this absolute value idea, and so here's L. And epsilon, so f of x minus L less than epsilon, we're looking at something like this, where this distance then is 2 epsilon, right? Because I'm either this way within epsilon or this way within epsilon. And now, so let's kind of draw that out there. Now, so for that epsilon, suppose C is there, then what we're saying is we can find a delta such that if x is within delta, and so here, that distance is 2 delta, because the absolute value, the difference, the distance here, has to be less than delta, so I'm on one side or the other. And so we draw this. What this means is that wherever f of x is in here, now I'm going to put a little dot here at C and L, because that's the limit part. But very importantly, what this means is if that limit exists, then I could zoom in on this rectangle. I could just fill up this rectangle, and I should be able to, no matter what I choose for the height of my rectangle, I should be able to adjust this down here so that my picture, now I'm going to draw it so that everything runs right into each other exactly. And I'll have that defined there, and I'll make a nice, easy, simple picture. But it says no matter how close I put these two together, I can build the vertical walls of this rectangle so that my function f of x always exits out the side, not the top or bottom. Okay? That's what this algebra up here is saying, right? Because it's saying that if, so given this epsilon, okay, so I draw that, I was given that, so I have to draw that, then I can set these bars, okay, I can pick the delta distance here, so that if I'm in there, then this absolute value, so f of x, right, minus L, there's the L part, so there's my f of x minus L, or here, f of x minus L, but I'd take the absolute value, that has to be strictly less than epsilon. Well, what that means in a picture is I can't go out the top. See, if this went out the top, well, let me draw it over here, right? If this went out the top like that, then there's f of x, there's the height there, there's L. This distance is definitely bigger than that epsilon distance I needed, right? If I take the difference here, that's bigger than the epsilon difference. So it can't go out the top. It has to go out the sides. Okay? So that is the formal definition. Now we're going to, I'll get some examples of this, and we'll work on some things here with the project. We aren't going to do lots and lots of problems this way, but let me show you the application here. And this is why, even if you're a chemist or a biologist, an environmentalist, or somebody like that, if you're using particular equipment, okay, if you're using particular equipment or particular measurements, right? So I want to take a reading of something and maybe or get a measurement, and then I'm going to multiply that measurement or square that measurement and so forth. Well, sort of what happens is my input can have errors. Now, I mean, they may not be big errors. I mean, you just may know, like if you're using a yardstick, but it doesn't have anything but yards on it. It doesn't have inches or feet or anything like that. It only marked off at yards. Well, then you can measure something. It might be something quite big and all that, but you can only be within sort of plus or minus 1 yard, right? You're gonna, because you don't have any other measurements on there, and so your input can have errors because of that. It can have errors because, if I set a yardstick end to end and so forth, I might build up some errors. So your input can have errors, right? And then, but your output, whatever you get out of this, has a given tolerance or error requirement. Tolerance requirement. Okay, we'll set up some nice, more concrete examples of this, but basically it comes down to, f of x is your output, okay, and x input. Okay, so required accuracy for f of x, your output, implies, well, in epsilon, we'll make sure, that's epsilon there, epsilon, required accuracy for x, the f of x, the output there, implies delta, a forced accuracy. I've got a bug running around me here. Accuracy for x, right? If my error measurement in x is off by 100 feet, but I'm gonna square this measurement. Maybe I'm looking at area, right, of a square, and so I'm off by 100 feet here. Well, when I square it, right, I'm off by 100. Well, that means I'm off by 100 there. I'm now off by 10,000 square feet, right? That's a problem. And so the question would be, well, if my area needs to be within a foot, well, how accurate do I have to make the sides? Right? That's the question. And that's really what's happening here, right? If this measurement here is my area, and I'm going to say, well, I have to get that, for whatever my answer is, I need to know that this accuracy is only, say, off by a square foot. Well, then how accurate do I need to be on my input measurements here before I square it? Oh, yeah, that is important. And all that is actually is an application of this definition of a limit. So that's how we're going to approach that. We're going to approach this idea, the calculations needed to kind of work with this, but we're going to put it in a applied context of input and output errors and tolerances and so forth. Okay, so that's what we're doing for that. So we'll come back to that with the project. Okay, so we'll come back to all this stuff with the project. We won't have homework that really has us do this, but I think it's important to see that there is this very formal definition, and it works like this. And if we go back to my example of the y equal x, where we kept putting these dots like this, well, think about it, right? If this can't have that limit at 0, because when I draw this box like this, because these dots get closer and closer together up here, there is no width around 0 that I could make my delta that I don't have a dot sitting outside of this box. That's a problem, right? I've got stuff outside of this box, and so even though it's not a nice continuous line, right, blowing up that box, what's happening is, oh yeah, great, it looks like I'm coming in here, but then all of a sudden, oh, I'm up there. And then I'm back in here. Well, so I didn't actually exit out the side, right? I exited like that. And I did it again even closer and so forth. So that is why those big oscillations fail. That is why dots like this up here, that as I get closer and closer to 0, they're always still there because they got closer and closer together. Now, along those lines, if I had done something more like, f of x is 1 when x equals 1/2, and that was it, and x otherwise, well, now, as I'm coming in here, well, once I get past, if this is 1/2 and I jumped up to 1 up here and there's a little hole there, well, that's fine at 0, because now as I make, even here, if I make this box that big, well, just choose my delta, so I make the box that big and I exit out the side, and the same thing down here. Exit out the side. So, that's why if you look at that definition of what a limit is, that formal definition, and think about the oscillation example or the dot example I did, this is the problem. That's why it's not working, because these dots are always getting closer and closer. So no matter how tiny I make that delta, I still have dots up here outside the box. Whereas down here, where I just said, well, x equals, at x equals 1/2, you get 1. Oh, that was one spot, it came up here, but I'm interested in 0, and so I can still do the box. And actually, at that point, it's still not a problem, because remember that definition said, oh, well, okay, except possibly at one point, the point itself that you're taking the limit. And so here, everything's centered, and when you draw that box, even though maybe this point is either undefined or out here, everything except that point does exit out the sides. So there's some definite subtle points about this formal definition, but they're not that bad. Okay, I think if you think about drawing the box, and you always have to draw this part first, and then you have to be able to make the width such that things go out the side. Then if you can always do that, no matter how small you make the horizontal lines, as far as how close they are to where you want the limit, you expect the limit to be, then great, the limit exists. All right, so that's our formal definition of limit, and that visual graphical interpretation of what it means. And now that's my plug for understanding all languages of math. So understanding the graphical, great. I mean, you can get that picture, I can talk about it, and you go, oh yeah, that makes sense. But what you need to be able to do then is work at getting to the point where when you read something like this with all the algebra and symbolism, you can translate it to a picture like this, and that's when that helps you then understand the symbolic algebraic language. Okay, so they're both saying the same thing. However, if I just draw the picture, that's not, there's room for error in drawing, room for error in interpretation, and so forth. And that's why we like mixing this English with the symbolism of mathematics. But that's a language, and it's a language of mathematics, just like the graphical is a language of mathematics. But they're different languages of mathematics. And what you want to become good at is work on that, being fluent, to go back and forth. And actually, the more you work on that, the more fluent you become in each part of the language, because each lends some insight to the other. Okay, so the better I understand the algebraic stuff, the more likely I can then translate it to the graphical, and vice versa. The better I understand the graphical, the more likely I can translate that to the algebraic. And when I can go back and forth, then I actually maybe understand a little mathematics. Okay, so we'll call that video done.